Thank you, Elizabeth, for a very warm introduction. And I like also to thank all the organizers for allowing me to be here. It's very lovely, not only a conference week, but all the time I spend here. It's quite nice, and I hope the week which is ahead of me will be also very nice. So looking forward to it. Today's topic I prepared for you is actually closely related to what you've seen already in the first presentation, but there are some differences. Mean distance in polyhedra. Well, so let me start with very simple introduction. You again have a convex body. Actually, in fact, it doesn't have to be convex, but I will stick with only convex bodies for right now, which is of dimension d, although I will only work in dimension 2 and 3, so okay, so in general, dimension of this body is d, and you select two random points uniformly, the points x and y, and you are interested in the mean distance between those 2 points. The distance is denoted with the norm of their difference, and to make it invariant with respect to scale parameter, I divide the whole thing by d's root of the volume. Now, if you enlarge the setting, so if you enlarge the body by some parameter, this value of lambda k stays the same. But in the case of distance is not a fine parameter. So you have to scale it by some factor and not affinely. You cannot make an affine transformation. Okay, so in this table I listed the results for which the mean distance was already known. And obviously the ball is actually very simple to derive, actually in any dimensions. And the other solids, for which the mean distance was known in 3 dimensions, was only the cube. So I was interested in the exact values for other solids as well, because I found quite strange there are no exact results. So then I created a numerical, well, it was not algebraic program in Mathematica software, and I was able to calculate all the solids, all the Platonic solids, which are often called regular polyhedra, tetrahedron, octahedron, well, what about dodecahedron and icosahedron? Well, I also found the exact mean values of the distance, but they are just, they are quite scary. But you can do it. And I would like to present you not only the results, that would be not so interesting for you, because you would like to learn something, I suppose, in this program. So I will see the method I used. I call it Crofton Reduction Technique, but it has no proper name. I just want this technique to be distinguished from another Crofton's formula, which is out there, which you probably know, Crofton's integral formula. But this is not the only Crofton's achievement. He actually came up with this reduction technique, which is also maybe known for a lot of you. But let's just go quickly through the technique. So imagine you would like to calculate some mean value of some function p, which is dependent on 2 points, where one point is chosen from some body A, and the other one is selected from a body B. Then if there are some conditions satisfied for this function p, the only condition in fact is homogeneity, which means that p scales with some parameter, so it looks like a distance to the power p. For example, now your p function scales with a factor of p. Then you can use this reduction technique, which means you shift the points to the boundary of those solids. So instead of calculating the mean distance of 2 points in the interior of A and B, you calculate the mean distance of the point being on the boundary of A, and Y stays in the interior. And then you switch those points, and the linear combination of it gives you the actual mean distance between 2 points in the interior. You can write it elegantly with this very simple equation, which states that P times and PAB stands for mean value, or the expected value of the function P, where you select x from A and y from B uniformly and independently. So this notation means you select your point from the boundary of A, and the other point is selected from the interior of B. Actually, there is a catch. It's actually not uniform on the boundary of A. It's weighted, so it has to be weighted first. And the weights are essentially the support function. So maybe you've seen this formula already, but I use this formula to calculate the mean distance for any polyhedron, regular polyhedron, but it could be replicated for any polyhedron in 3 dimensions. So there is also a generalization. If you have more points, you shift one point to the boundary, then the next point, then the third point, and so on. And again, it's some linear combination of those mean values. You get the original mean value of P. Let me show you an example, which is in 2 dimensions, in order to calculate the mean distance of 2 points in a square. So the first step would be to move the point or shift the point to the boundary, first point. And then, well, I forgot to mention one crucial assumption which allows you to use this reduction technique. Well, let me go back for a minute. This crucial assumption is this one. You can use it only if there is a point C which lies in the intersection of affine holes of those 2 regions from which you select those points X and Y. I call this point a scaling point because the proof actually involves scaling the whole setting, and then you somehow recognize that in larger setting you have the same mean value. So this is the basic idea of the proof. So for this configuration, let's call it a configurations. For this configuration, you can select your scaling point to be here in the bottom left corner. Then you shift this point or move this point to the boundary. Or there are actually 2 other possibilities. What you can do, you can move the point 2 to the boundary, either up or to the right side of the square. So you get 3 configurations out of this configuration.
Can you explain the very first step in this reduction? So the I, for example, this horizontal line.
This first one? Or?
Yes, exactly. What is done there?
What is done there? Well, there is your scaling point C. And at the first step, you move one of the points to the boundary. And since the mean value is the same if you put one of the points on the left side or the right side, it doesn't matter. So you can put it only on one side of the square.
And then which kind of expectation you need to compute after that?
You only need to, well, let's focus on this.
Of x minus y, right? And after that, you have to compute what?
Well,
sorry, I just want to understand.
Well, that's completely okay. So, for example, if you are able to reduce the configurations to find the other configurations which are in there, you only need to compute the mean distance between a point located on one side and a fixed point, and between 2 points which are located on opposite sides of a square. Uniform. Uniform, yeah. And in fact, this mean value of P, which you can treat as a mean value of distance or any power of distance, is just a linear combination of mean values between a point located on one side. Well, this notation is, I use this notation. P, instead of writing PAB, I use lower a and b and lower b, where those lower letters are they mean dimension of the regions where the points are selected from. So this P10 stands for mean value where the first point is selected from a one-dimensional subspace located somewhere. It has to be defined with respect to a context, so you need to know what does it mean. So P10 is actually this mean value between the point located on one side and a fixed point. P11R is the mean value between 2 points located on the opposite side. Mean value of a distance to power P. Is that understandable as an answer, or?
In the first, in the case P10, you can take the point on the side on any of the four sides.
No.
Cannot be on the adjacent.
This point 0, cannot be located in here. Well, there are some hidden assumptions, but I wanted to avoid those. The assumption is you only move the points outwards where the scaling happens. This is loosely speaking. So, for example, if your scaling point C is here, the point 2 cannot be moved to this or that side, the upper or the left side, only to the bottom side or the right side, which corresponds to this configuration.
I think what we are wondering is why. Like, what's the main idea behind? Like, I get the general frame, but
okay.
How is it possible to go from one step to the other? Like, what is that guarantees that you can do that?
Maybe it's possible to explain the very first equation. You had P22 is equal to something. Maybe we understand that. We understand.
Right. Well, okay.
How to explain the very first?
Let's P be L to the power P, where L is the distance between 2 points, and you raise it to power P. Then PAB is the mean value of the distance to the power P.
We can assume P equals 1, for example, for simplicity.
Well, okay, P equals 1. So you write down this equation, and this equation tells you that mean distance between 2 points selected in the interior is a linear combination of the same distance and the mean distance of 2 points where one of them is selected on the boundary.
And why? Why is this the case?
Because of this lemma. Let's assume this. Let's assume the lemma is true, and you can always move the points to the boundary. So mean distance between 2 points in the interior is related to the mean distance where you shift one of the points to the boundary. And the key idea I used is to use that repeatedly, which is not so often done in literature, unfortunately. And so this is the diagram of configurations I got when I used this lemma repeatedly. And you can solve this linear system of equations related to each reduction, which is denoted with those Roman capital numbers. And you can only, in order to calculate mean distance between 2 points in the interior, you only have to calculate the values for these two configurations, which are very simple. Because in order to calculate this configuration, you would need to integrate, you would need to have 4 integrals, because there are 2 degrees of freedom for each of the points. But in that case, there is only 1 degree of freedom, and there are 2 degrees of freedom, but there is a shift invariance. You can shift all those points by the same amount, and you can integrate it out. So again, you get an integral with 1 parameter. So from this, you can actually deduce all the moments of the distance between 2 points in square, which are now a function of, well, what's that? I think it's called hypergeometric function. Probably all you should know this function. And if you, well, and the very nice consequence of this, I discovered during past week I was spending here at Bonn, is that you can in fact very easily extract the distribution function out of it. Just use IMT and you are done. Well, I hope all of you know what IMT stands for. It's inverse Mellin transform. So you can in fact deduce the distribution from the moments by using inverse Mellin transform. This distribution is, however, known, but I will show you what is not known. Let me mention that exact, well, this is P22, which stands the moments of distance. These moments of the distance are actually known in regular polygons of any number of sides, exactly. And this result is quite, it's not my result, but it's a very recent result. I was interested in mean distance in polyhedra, so you go 1 dimension up. So the only difference is that you get more configurations. So this is the list of configurations for the cube. And as you see, you would have to compute a 6-fold integral in that case. But in the end, by using these reductions, you can express the mean distance using mean distances over simpler regions. I also did that for an octahedron. This was actually known, this value of mean distance. It's called the Robbins constant. But it was not known for an octahedron. And for a tetrahedron, I also was able to write it explicitly for any power of p, not just for p equals 1. So for a tetrahedron, I was able a few days ago to find the distribution function as well, but that's I don't think it's worth publishing because it's just distribution function. No one will be ever interested in it. So there is a very nice example I would like to show you in the last 5 minutes I have. And if you want, I can also show you the reduction for dodecahedron. There are in fact 30 configurations, and you have to calculate all of them. It's very hard to proceed through. And my paper, which is on the calculation of those mean distances, is actually 50 pages long because of all those configurations. It's very hard to proceed through all of them. But nevertheless, let's move on. Another problem in convex geometry might be to find the mean area of a triangle. So you have a convex body and you are interested in the mean area. In fact, this is known for any 2-dimensional polygon, okay? But in higher dimensions, no result is known, except, of course, the ball. So no polyhedron has its mean value of random triangle inside, expressible in an exact form. And I would like to show you how to calculate the mean area of a triangle inside a triangle. I think it's a very nice example, which turns the problem of solving 6-fold integral into a kindergarten problem, I would say. A very easy one. So the first step, you reduce this by moving the point to the boundary, and you get one equation. Then you reduce it again, you select your scaling point and move either this point to the boundary or one of these interior points. You get two configurations. Again, you perform this task of reduction, you select your scaling point and move the points to the boundary. But the problem is that now you are stuck because these configurations are irreducible. You cannot find the scaling point C because the intersection of affine holes of these three sides is empty. But there is a trick how to calculate mean area if you select these 3 points on the sides. Well, first let me write down what's the mean area so far. It could be written as a linear combination of those mean areas. For the first configuration, you can make a following trick, which is very simple. Let's denote those 3 areas as S, which you are interested in the mean of S prime, S double prime, and S triple prime. Their sum is, of course, 1, so you take the mean of this equation, and suddenly the mean area S11, so its mean area of this triangle, is 1 minus 3 times S mean area of S prime. And this configuration is reducible again, so we reduce it, and you are left with this mean area, which is actually very simple because it's 1/2. But you can again make this trick because these are actually the same, and you get that this S100 is 1/2. In the other case, the other example is not so trivial, but the computation is not hard. You use conditioning. So in order to calculate the mean area of S, it's the same as fixing the area of RPY triangle and condition with respect to this area, which I called S prime. Then this mean area of S is a multiple of mean area of a triangle which is S200, this configuration, because you can finally scale this setting, PYR triangle to this triangle, times the area of this triangle. And the other possibility is that X is located on the other side of this line PY, so you have to write it symmetrically. Then you calculate the expectation of S prime. S prime is in fact that configuration S110. You get 1/3 because it's an integral of x squared from 0 to 1. And this S22 is also very simple to use. You can also use this simple technique, writing this, this configuration, let me explain. These 2 points are fixed, and this point is selected from a region of dimension 2, which means from this interior. And you can deduce that this mean area is also 1/3. And now you have it. So this is your mean area deduced backwards from originally where you have started with. And you have already seen this value because 4 times 1/12 is 1/3, and which is one of the Sylvester's answers you saw earlier. Well, I also was interested in triangle obtusity, but I don't think we have time to discuss that. Probability of triangle being obtuse is also a homogeneous function, because you can scale the setting and the probability stays the same, so little p is equal to 0. And you can again write down some reductions, and you can compute this probability in various cases. For example, in triangle, this value hasn't been known, so I was able to reduce, this is the probability. And actually for a cube, you can get something. I discovered that in fact there are like 10 to the power of 5 integrals in order to solve that. And when I solved one integral, actually it was not me, I put it on math stock exchange, and somebody solved this one particular integral. It looked like this, so I assumed this probability of triangle being obtuse in a cube will include this Catalan constant. That's my conjecture, but you will see. So for a rectangle, this obtusity probability is actually known, where A is the scalar ratio. So when A is equal to 1, you get, of course, probability of triangle being obtuse in a square, which you saw in that table. And for a triangle, you can do this reduction technique and solve all of the resulting integrals, and you get something like this. It's very unlikely, but you can do it. Where alpha, beta, and gamma are the interior angles of the triangle you are selecting the points from. I was also interested in other problems, but I don't have time for it, so thank you.
Questions? Yeah?
Is there any upper or lower bound for the lambda k?
Are there bounds?
Upper bound and lower bound.
I am not sure. It's a highly theoretical question, and I was not able to answer that. I only know that you can compute it exactly for polyhedra, but actually the upper bound and lower bound for the mean distance in polyhedra is known. It's a result from Kablushko, Gusakova, Monet, and Tele. It's 2 years ago. It was published 2 years ago, I think. These 2 bounds for mean distance.
Other questions?
When you use like the reduction technique for 3 points, is it that, I mean, maybe it is it that immediate to, because the formula you gave at the beginning, the reduction technique was for 2 points. Yeah. Going for 3 points, is that immediate just by conditioning, or are there some issues?
That one.
Yeah, here, like, because in the previous part, in the previous reduction steps, you had just 2 points, now you have 3 points. So is that immediate that you can extend the process to 3 points, or am I missing something? You had...
Short answer would be yes, you can
okay.
It for any number of points.
Okay, thanks.
More questions?
Any further questions? Or I can later show you the diagrams for dodecahedron if you want.
Okay, so we thank you again.